Have you ever wondered how those tiny images on film strips are magnified for display on the big screen? Later in this lesson, we consider images formed by lenses. But first, let's investigate just how mirrors form images. We can use the principles of reflection and refraction that we covered earlier to make graphic images with a computer. But what happens in the real world? Let's consider the reflection of a small object in front of a flat mirror. Incoming or incident light waves hit the mirror and reflect off the mirror according to the law of reflection. Recall that the law of reflection states that the angle of reflection is equal to the angle of incidence. If we extend the paths of the reflected rays through the back of the mirror and beyond, the lines meet at a single point behind the mirror. This point is called the mirror's image. This image, known as a virtual image, is what you see when you look at yourself in an ordinary mirror. The image is called virtual because the image appears to be behind the mirror, even though no light actually reaches behind the mirror. Though the image is called virtual, this term does not mean that we cannot see the image. When we look at an object in a mirror, our eyes intercept only the rays reflected from it. Our brains interpret them as an image of the object behind the mirror. Notice that, for a flat mirror, the distance between the image and the mirror, known as the image distance, S sub I, is the same as the distance between the object being reflected and the mirror, known as the object distance, S sub O. The situation gets both more complicated and more interesting when the mirror reflecting an object is curved. With curved mirrors, the reflected images may be different in size, position, or orientation, or all of these, than the object being reflected. When curved mirrors are involved, using the law of reflection directly to trace the rays becomes very difficult. We need another method to achieve this. Consider the mirror illustrated. Because the light hits it on the side that curves inward, it is called a concave mirror. You can remember this by imagining that the mirror forms a small cave. If the reflecting mirror is parabolic, when incident or incoming light rays that are parallel to the axis of the mirror are reflected by the mirror, the reflected rays meet at a single point. This point is called the focal point. The distance between the focal point and the mirror is called the focal length and is denoted by lowercase f. Because the light converges, concave mirrors are also called converging mirrors. Conversely, light that approaches the mirror through the focal point is reflected parallel to the axis of the mirror. In practice, parabolic mirrors are hard to make, so we use spherical mirrors instead. As long as we use only a small portion of the sphere, the mirror is very nearly parabolic, and the focal length is simply half the mirror's radius of curvature. Which of these mirrors has the shortest focal length? Correct. The mirror with the smallest radius, and thus the most curvature, has the shortest focal length. Now we'll begin to trace rays to find the position of images formed by the mirror. In reality, light leaves the object in all directions and reflects off all parts of the mirror. However, we will trace just a few special rays that are easy to show, and then use them to find the location of the image. It is convenient to use an upward pointing arrow as our object. The image then will be shown as either an upward or downward pointing arrow. The tip of the arrow indicates where the rays cross, and the base of the arrow lies on the axis of the mirror. First, we consider a single ray of light that leaves the object parallel to the axis of the mirror. Because this ray that approaches the mirror is parallel to the mirror's axis, when it is reflected, it must pass through the focal point. Next, we consider the ray that leaves the object and passes through the focal point of the mirror. When it reflects off the mirror, it must be parallel to the axis. Generally, the two rays we have considered are sufficient to determine the location and orientation of the reflected object's image. But there are two other sorts of rays that can be used to check our answer involving two other sorts of rays. The first check is to draw the ray that hits the center of the mirror, and then, using the law of reflection, draw the reflected ray. The second way to check is to draw the ray that passes through the center of curvature. This ray will be perpendicular to the mirror and thus will reflect directly back along its original path. This ray, while simple and helpful, is often the least accurate of the principal rays. Let's review what we've covered here. There are four principal rays. The first ray is parallel to the axis as it approaches the mirror and is reflected back through the focus. The second passes through the focus as it approaches the mirror and is reflected back parallel to the axis. The third ray strikes the center of the mirror and is reflected back in accordance with the law of reflection. The fourth passes through the center of curvature and is reflected directly back out, following its ingoing path. If we put a screen, such as a thin piece of paper, at the point where the rays cross, an image forms on the screen. Because the rays actually cross at that position, the image is called a real image. Notice that the image is upside down or inverted. This is a general property of real images formed by a single optical element. The image is also closer to the mirror than the object being reflected is, and it is smaller than the object. Thus, such an image is described as real, inverted, and smaller. Accordingly, we describe an image from a flat mirror as virtual, upright, and the same size. Suppose we have a mirror shaped like the outside of our last mirror, reflecting light off the outside surface. Such a mirror is known as a convex mirror. Parallel light that approaches the mirror cannot converge to the mirror's focus, because the focus is on the far side of the mirror. Instead, the light reflects as if it has come from the focus and diverges outward. Notice that if we extend the paths of the reflected rays backward through the mirror, the lines meet at the focal point. Because the rays reflected by this kind of mirror diverge, convex mirrors are also called diverging mirrors. As you might expect from our earlier discussion, rays moving towards the mirror that are heading towards the focal point are parallel to the mirror's axis when they are reflected back by the mirror. Here again, though these rays are directed towards the focus as they approach the mirror, they are reflected before actually reaching the focus. Convex mirrors have four principal rays of interest. The first ray approaches the mirror parallel to the mirror's axis, and its reflection moves from the mirror as if it had been reflected from the focal point of the mirror. The second ray approaches the mirror in alignment with the focus and reflects along the line through the point of reflection and parallel to the mirror's axis. The third ray approaches the mirror and reflects from its center, such that the angle of approach equals the angle out, relative to the axis of the mirror. The fourth ray approaches the mirror along a line perpendicular to the mirror's center of curvature and reflects straight back, retracing its incoming path. Notice that the reflected rays do not cross. However, if we extend the lines back behind the mirror from their points of reflection, they do cross. Thus, this is a virtual image, because the rays leave as if they had crossed at a point, even though none of them actually reached that point. The image created is virtual, upright, and smaller than the object. In general, images from a concave or diverging mirror will be virtual, upright, and smaller than the original object. So far, we have used ray tracing to find and classify images formed by spherical mirrors. However, much can be gained from a mathematical approach to this subject, especially when used in conjunction with the drawings. Ray tracing helps develop physical intuition, while math helps quantify the phenomena. The first equation simply states that the focal length is half the radius of curvature as we previously mentioned. The second equation shows the relationship between the distance from the object to the mirror, the distance from the image to the mirror, and the focal length of the mirror. Each of these distances is positive in cases when the light actually reaches the described point, whether it be the object, image, or focus, and negative when, instead, reflective rays converge behind the mirror to form a virtual image. Thus, a virtual image has a negative image distance because the light rays don't extend to a real image. A convex diverging mirror has a negative focal length because the light rays never actually reach the focal point. The object distance is almost always positive because the light actually originates at the object. Be careful when using this equation. Solving for the focal length cannot be achieved by simply inverting the object distance and image distance terms to solve for the focal length. Let's work an example. Suppose an object is placed 10 centimeters in front of a mirror with a radius of curvature of 8 centimeters. Where is the image? First, we find the focal length to be 4 centimeters. Next, we solve the equation for the image distance and plug in the values and find that the image is 6.7 centimeters from the mirror. Because the distance is positive, the image is real. Now consider the third equation. The first part simply defines the magnification m as the ratio of the image height h sub I to the object height h sub o. The sign of m indicates whether the image is upright or inverted. M is positive for an upright image and negative for an inverted image. The magnitude of m indicates the relative size of the image compared to that of the object. If the image is larger than the object, the absolute value of m is greater than 1. If the image is smaller than the object, the absolute value of m is less than 1. The second part of the equation relates the image magnification to the image distance and the object distance. Notice that if both the image and the object are real, the magnification will be negative and the image will be inverted. Returning to our example, suppose the object is 6 centimeters high. How tall is the image? By rearranging the equations, we find that the magnification is negative 0.67 and that the image is 4 centimeters and inverted. This chart can be used to determine quickly where an image will be positioned and what its relative size and orientation will be. Now let's put this information to work with a simulated mirror experiment. So far, we have used ray tracing to find and classify images formed by spherical mirrors. However, much can be gained from a mathematical approach to this subject, especially when used in conjunction with the drawings. Ray tracing helps develop physical intuition, while math helps quantify the phenomena. The first equation simply states that the focal An object sits in front of a spherical mirror as shown. Try and match a set of desired image characteristics by repositioning the object relative to the mirror's focal point and radius of curvature. Once you have matched the image characteristics, determine the image distance and the magnification factor of the image. Move the object along the center line to the desired position and click on the Submit Position button. Two principal rays will then be drawn based on the object's position to form the image. Use the object's distance from the mirrors S0 and the mirror's focal length f to calculate the image distance Si and the magnification factor. Click and drag the object to reposition it. The object position you selected does not create an image with the correct characteristics. Please try again.
Your answers are incorrect. Click on the answer again. Good job! Your answers
Optical images can be formed by the refraction of light through lenses. A lens is simply a piece of glass, plastic, or other clear material that is curved on one or both faces. The curves cause light rays passing through the lens to bend. The bending of light by a thin lens can be described by fairly simple equations. The bending by very thick lenses, however, is very complicated. We will consider thin lenses in this section. A thin lens is called thin because its thickness or width, W, is very small compared to its diameter, D. Light rays passing through a thin lens behave in a specific fashion with regards to the focal points of the lens. One kind of thin lens is a converging thin lens. When light rays that are parallel to the axis of a converging thin lens strike the lens's surface, they are bent in such a way that they converge at the focal point on the other side of the lens. Light rays that pass through a focal point before striking the converging lens are deflected by the lens to a path parallel to the lens axis. In a diverging thin lens, the roles of the two focal points are reversed. When light rays that are parallel to the lens axis pass through the lens, they are deflected to diverge as if the light came directly from the first focus. Light rays that initially are directed towards the far focus are turned outward by the lens and move on parallel to the lens axis. Converging lenses are often convex on both sides. That is, they curve outward on both sides. However, one side can be flat, or even concave, as long as the lenses are thicker in the middle than at the edges. This thickness ensures that the convex side dominates the deflection of light rays. Diverging lenses are often concave on both sides, giving them an hourglass shape. However, one side can be flat or even convex, as long as the lenses are thinner in the middle than at the edges. If we have a thin lens, the effect of one or both of the concave sides ensures that the light waves will diverge or move away from one another. Now that we know what features make up a converging or diverging lens, let's see what determines the value of the focal length, f. What do you suppose will happen to the focal length of this lens if we increase the curvature of the lens? Correct. As the curvature increases and the lens gets thicker, the focal length decreases. This is because the light hits the lens at a greater angle and therefore refracts more. This is true for both converging and diverging lenses. Now let's study image formation by a lens. As we did for mirrors, we will locate the image by tracing certain principal rays that are easy to find as they move from a single point on the object. Remember, however, that though we consider only a few principal rays here, light rays from this point strike all parts of the lens, and all of them contribute to the image. Let's examine the first principal ray. The incident ray is parallel to the lens's axis, and the reflected ray goes through the focus. With a converging lens, the light ray travels through the focus on the far side of the lens. A diverging lens bends the parallel ray, and the ray then leaves the far side as if it came from the focus on the near side. Now let's look at the second principal ray. The incident ray is aligned with the lens's focal point, and the reflected ray is parallel to the lens's axis when it leaves the back side of the lens. In the case of a converging lens, the incident ray passes through the focus on the near side of the lens. In the case of a diverging lens, the reflected ray passes through the focus on the near side of the lens. In general, these two rays are enough to locate the image. However, if the two focal points are the same distance from the lens, a third principal ray can be drawn.
This ray extends from the object and passes through the center of the lens where it meets the lens axis. Because the ray goes through the center of the lens where the two lens surfaces are parallel, it does not bend. The image produced by the converging lens is now obvious. In this case, it is a real inverted image that is bigger than the object. For the diverging lens, the image is slightly more difficult to find. Because it is a virtual image, we must trace the outgoing rays backward until they cross. This reveals a virtual upright image that is smaller than the object. Keep in mind that we considered only two simple examples of image production by lenses. In this case, the image from the converging lens was real, but sometimes images from converging lenses are virtual. Finding them will necessitate tracing outgoing rays backward. Except for the equation relating frequency to mirror radius, the equations we use for mirrors also apply to lenses. As with mirrors, the focal length is positive for a converging lens and negative for a diverging lens. The image distance is positive if real and negative if virtual. The object distance is almost always positive. Lens magnification is positive if upright and negative if inverted.
Therefore, we can see that the lens equation and the mirror equation are used in exactly the same manner. In addition, the chart summarizing the image's location and magnification is identical for lenses and mirrors.
We now know how to find and describe the images created by a single lens. But what happens when two or more lenses are involved? In such cases, the image of the first optical element serves as the object for the second lens. Notice that process produces an upright real image. A wide variety of optical instruments, such as telescopes and microscopes, take advantage of image produced by combinations of lenses and mirrors.